Hey guys, we're going to continue looking at buffers. And just kind of a reminder, a buffer is any solution that contains something that can absorb hydrogens, acting as a base, and something that can absorb hydroxides, acting as an acid, that can act as a buffer. So it has to have something that can do both, or else it's not considered a buffer. So here's a couple examples of things that we're going to look and see, can they be buffers? So remember, you have to evaluate and see if there is a substance that can absorb the hydrogen from an acid and then the hydroxide from a base. So looking at our first example, where we have 0.1 molar potassium nitrate and 0.1 molar hydrogen or nitric acid. So here, with the potassium nitrate, well, if it tried to absorb hydrogen, it would make nitric acid, which is a strong acid, so that would not work. If it tried to absorb hydroxide, it would make potassium hydroxide, which is a strong base. So this cannot act as any part of a buffer. Check the nitric acid. This is a strong acid. So if you remember that strong acids tend to not be in buffers, then this will not be a buffer situation because it cannot dissolve the hydrogen or hydroxide. Look at our second example. We have 0.1 molar sodium nitrite and 0.15 molar nitric acid. Nitric acid, remember, is a weak acid. So weak acids can absorb hydroxide, but we need to see if something in the sodium nitrite can absorb hydrogen. Well, if you split this down the middle, the nitrite ion can absorb a hydrogen to produce nitric acid. So one substance will absorb hydrogen, producing a weak acid, which is fine. And then we have a weak acid that can absorb the hydroxide, so this will be considered a buffer solution. Look at our third example. We have 205 milliliters of a 0.1 molar acetic acid solution and 0.5 grams of potassium hydroxide. Here, the acetic acid is a weak acid, so it can absorb hydroxide. Whereas potassium hydroxide, this is a strong base, but if you look, the base will absorb hydrogen ions. So this can be considered a buffer. Look at our next example. We have 0.1 molar sodium carbonate and 0.05 molar sodium phosphate. Our sodium carbonate, if it tries to absorb hydroxide, makes sodium hydroxide, which is strong, so it can absorb hydroxide. But the carbonate ion can absorb a hydrogen, acting as a weak base or weak acid, excuse me. Looking at the sodium phosphate. Sodium cannot absorb hydroxide because it's considered a strong base. The phosphate can absorb a hydrogen. We have something that will absorb hydrogen but not hydroxide. So this will not be considered a base. Look at our next sample. Here we have 0.1 molar ammonium nitrite. So remember, if we have one substance, if each ion can absorb the hydrogen or the hydroxide, there's no spectators that way, so it doesn't make a strong acid or strong base. That one salt can be considered a buffer. So if you look, ammonium, the NH4 plus, will attract hydroxide, and ammonium hydroxide is a weak base, so that's fine. The nitrite can absorb the hydrogen, producing nitrous acid, so this by itself is considered a buffer. Look at our last example. we have 0.1 molar sodium hydrogen phosphate. Now, sodium is positive. It cannot attract hydroxide because that would make a strong base. But remember, we have some of those ions that are considered amphoteric. So this H2PO4 negative is negatively charged, so it can add a hydrogen to become phosphoric acid, which is weak, but it can lose this hydrogen to react with a hydroxide producing water. So this is one of those amphoteric ions, so it will be considered a buffer, just using that same ion as our acid and our base. So that's what we covered in our last lecture. We're going to look at how to do calculations with buffers this time around. So here's an example, and we're going to go through each part individually to figure out how to solve for different pieces whenever we're talking about buffers. So we have a buffer that's made by adding 0.300 moles of acetic acid and 0.300 moles of sodium acetate to enough water to make a 2-liter solution. So it gave us a weak acid with the acetic acid, and then a salt with its conjugate base, that acetate ion. So this is considered a buffer. And then it wants us to find the pH of the buffer after some of the base is added, and then the pH if we had base in pure water, just for comparison to show you that the pH does resist a change whenever that base is added. Let's look at the first part. This one just wanted to know the pH of a buffer solution. So remember, whenever we're doing pH of a buffer solution, you can use the Henderson-Hasselbalch equation that's on your reference sheet of the pH equals the pKa plus the log of the base over the acid. And remember, with the Henderson-Hasselbalch equation, you are able to use moles of both acid and base. You don't necessarily have to convert to molarity for both of them. So based off of what we know, we would look up the Ka value for acetic acid, which is 1.8 times 10 to the negative fifth. And we would plug that in with pKa. Remember, the p is the negative log, plus the log of our base, which is 0.300 moles, over our acid, which is 0.300 moles, which gives us a pH of 4.74. One thing to note is whenever we have the same concentration of our acid and our base, that 0.3 over 0.3, it's going to give us log of 1, which is equal to 0. So whenever those two are the same, our pH is equal to our pKa value. So our pKa value, if you do the negative log of 1.8 times 10 to the negative fifth, is equal to 4.74. Let's go on to our next part. It wanted us to calculate the pH of the solution after 0.02 moles of base is added. So remember, if we add a base, it reacts with our acid, which allows it to absorb that hydroxide. For this, because it is a weak acid that you're reacting with the base, you need to set up an ice table. So our overall equation, whenever we add a base, is our acid combining with the hydroxide to produce our conjugate base and water. And look at the initial amount. So it tells us how much acetic acid we have initially and how much acetate ion we have initially. And it says that we're adding 0.02 moles of hydroxide, which is also an initial value. Well, since we are absorbing the hydroxide, we are reducing on the reactant side and adding to the product side. And we're trying to get rid of all of that base, so that entire 0.02. So that will leave us with equilibrium values of our acetic acid is going to be 0.280 moles, and our acetate ion will be at 0.320 moles after this has absorbed all of the base. So if we want to know the new pH, you can now plug these values into that same Henderson-Hasselbalch equation. So pH is equal to pKa, which was that 4.74, plus the log of the base, the 0.320, over our acid, the 0.280. And if you put that in the calculator, it gives you a pH of 4.80. So the pH did go up, but not very much. It only went up by 0.06 because that buffer was able to absorb that base. So the pH may go up slightly, but it's not going to jump a whole lot. And how you can see this is if we compare what this would look like to if we just added the base straight to water versus adding it to that buffer solution. So remember, sodium hydroxide is a strong base, therefore it is going to completely ionize. So the hydrogen ion or hydroxide ion concentration is equal to the concentration of the sodium hydroxide. So if we find that concentration, remember concentration is moles over liters to get that molarity. So the 0.02 moles over 2 liters is 0.010 moles or molar hydroxide. You can solve for pOH. Do the negative log of 0.01 to get a pOH of 2.00. And then to find pH, you do 14 minus 2, which gives us a pH of 12. So even though we added a base that was a pH of 12, it only moved the pH up by 0.06. Let's look at another problem. We have a buffer that's made by dissolving 14 grams of sodium nitrite in 500 milliliters of 0.250 molar nitric acid. So we have a weak acid with its conjugate base. It wants to know what is the pH of the buffer solution, and then write the chemical reaction that occurs when a small amount of hydrochloric acid is added to the buffer solution. So yet again, writing out that neutralization equation. First step is what's the pH of the buffer solution. So remember this, you can use the Henderson-Hasselbalch equation. But remember, Henderson-Hasselbalch, you either have to plug in molarity or moles. Well, we do not have molarity for both, but we have enough to figure out moles for both. So we can take the 14 grams of sodium nitrite, divide by the molar mass to figure out how many moles of sodium nitrite. So that would be equal to 0.2029. We can figure out moles of the nitric acid by doing the molarity times the volume. So that will give us 0.125 moles. And plug all of that into our Henderson-Hasselbalch equation with the Ka value of nitrous acid, which is 4.0 times 10 to the negative fourth. Plug that in the calculator, and we get a pH equal to 3.61. So yet again, we found moles of both, plugged it into our Henderson-Hasselbalch equation, and solved using the calculator. Let's look at the second part. This one wants us to write a reaction that occurs when a small amount of hydrochloric acid is added to the buffer solution. So you have to pay attention to which part of the buffer is going to react. So hydrochloric acid is introducing hydrogen ions, which is going to react with the base part of our buffer, which is the nitrite ion. And excuse me, I'm having to write on the computer. So we have the nitrite ion plus our hydrogen ion, which is probably going to be in water, so it'll be the hydronium, the H3O plus. Sorry, that's a 3. That always produces water. And since the water is giving up the hydrogen, that is being absorbed by the nitrite to make nitrous acid. So always pay attention to which part of the buffer is reacting. So remember, acid is absorbed by the base part of the buffer. Bases will be absorbed by the acid part of the buffer. And they will always end up producing water. Here's another sample we can look through. We have 500 milliliters of a buffer solution that is 0.50 molar ammonia and 1.8 molar ammonium chloride. And we have 3 parts. It wants us to find the pH of the buffer solution, to find the pH after 8 grams of base are added, and it wants us to find the pH after a 10-fold dilution of the original buffer. So let's address them one at a time. First part, find the pH of the solution. So it gave us molarity of our acid and molarity of our base, and they're within the same volume, so we don't have a difference in moles or anything like that. So we can simply plug these values into our Henderson-Hasselbalch equation. And the Ka of ammonium, or the ammonium ion, is going to be 5.6 times 10 to the negative 10th. Pay attention to whether you have Ka values or Kb values. You want to plug in that Ka. So we plug in the negative log of Ka, that 5.6 times 10 to the negative 10th, plus the log of our base concentration, the ammonia, over our acid concentration, the ammonium chloride. And that will give you a pH of about 8.70. So this is basic overall. Our second part of our problem wanted us to find the pH after 8 grams of sodium hydroxide were added to the solution. So whenever you're looking at that neutralization, you need to do an ice table. So since we're adding sodium hydroxide, we're adding hydroxide ions. So that's a base, which will be absorbed by our acid part of our buffer, which is the ammonium chloride. So they will interact with the ammonium ions. So we have the ammonium ions and hydroxide ions producing ammonia and water. Looking at our values we have initially, whenever you are trying to neutralize, you need to use moles. So you'll figure out moles of ammonia. So 1.8 molar times the 0.500 liters gives you 0.90 moles. If you take the 8 grams of sodium hydroxide, divide by the molar mass of sodium hydroxide, which is approximately 40, you get 0.20 moles. And for ammonia, you take the 0.5 molar times 0.500 liters, and you get 0.25 moles of ammonia. So anytime you're neutralizing, you do want to start with moles, which we had in some of our previous problems. Remember that we're trying to neutralize and get rid of all of this base, so we will be subtracting on our reactant side. If we subtract the 0.20 from the reactant side, add 0.20 on our product side, we have neutralized equilibrium values of, for ammonium, 0.70 moles, and ammonia 0.45 moles. And remember, since we have moles, those can go straight into the Henderson-Hasselbalch equation. So we would have our negative log of Ka plus the log of the base over the acid, which will give us a new pH of 9.06. So it did go up by 0.36, I believe. So not by too much. The third question's a little bit trickier. The third question wanted us to calculate the pH after a 10-fold dilution of the original buffer. Now remember, our original buffer had a pH of 8.70. If you dilute the buffer, it's going to change the concentration of everything, but it's not going to change the number of moles that were initially present. So if you dilute a buffer with water, it will not change the pH at all. So the pH will still be 8.70. So note that anytime water is added to a buffer, it does not change anything. We're going to look at how effective buffers are. So some buffers are going to work better than others, depending on how much of that buffer solution is present and how much acid or base it can absorb. A good buffer should be able to neutralize moderate amounts of added acid or base, so 1 drop is not going to make a difference in the pH, generally. But if you add 500 milliliters, it's probably going to change the pH of it. The effectiveness of a buffer depends on the relative amounts of acid or base and the absolute concentrations of acid or base. So how much are you adding and how strong are their concentrations? A buffer is going to be most effective when the base to acid ratio is 1. So when you have equal amounts of your acid or base, so equal moles of your acid and base, is where it's going to be most effective. It's going to be able to absorb the most acid and the most base when that ratio is equal. And a buffer is considered effective when the base to acid ratio is between 1/10 and 10. So it's okay for the ratio to be different, but you don't want like a 20-to-1 ratio. It's not going to be as effective because it's going to absorb only one type of substance. So here's kind of what we're talking about. You may have differences in buffers. So here's an example of a concentrated buffer where you have a lot of particles in that same amount of space, and a dilute buffer. So it's the same volume, but not as many particles. So this is going to have more water added to it. A concentrated buffer is going to be able to neutralize more acid or base than a dilute buffer simply because there are more particles present. The more particles there are, the more it's going to be able to dissolve some of these substances. All right. Looking at buffer effectiveness, and if you're in the presentation, you can actually click on this and it will check your answers as you go. So it says that you have 2 solutions. You have a solution A that's a buffer with the 0.10 molar H2PO4 and 0.2 molar HPO4. You also have solution B, which is the same substances, but the H2PO4 is at a 0.15 molar and the HPO4 is at a 0.3 molar. So it says, what's true about the pH of these solutions? Well, if you look, they both are going to be acidic. They're both going to be the same substances. They're both the same ratio. This is a 2-to-1 ratio and a 2-to-1 ratio. So their pHs would essentially be the same because the ratio is going to match. It wants to know which solution will be able to neutralize the addition of 0.11 molar hydroxide. So remember, hydroxide is going to be absorbed by the acid, which is going to mix with our one with more hydrogen. So over here, the 0.10 molar H2PO4 in solution A is not going to be enough to dissolve 0.11 molar hydroxide. But in solution B, you have 0.15 molar H2PO4, which can neutralize 0.11 molar hydroxide. So this second answer should be solution B. The third question wants to know which solution will be able to neutralize the addition of 0.11 molar hydronium. So this is our acid, so it's reacting with the base part. Well, if you notice, both of these values are above 0.11. So both of these will be able to absorb that much acid. And then last question, want to know what's true about the buffer capacities of these solutions. So remember, the more particles, the more it's going to be able to neutralize. So since the molarities in solution B are higher, they will have a better buffer effectiveness. That one will be able to dissolve more of any substance that's added in. Let's look at how you're going to prepare a buffer solution. This we'll do in a lab situation pending our return to school. So buffer, we said, is considered effective when the base to acid ratio is between 1/10 and 10. And the effective range of a buffer is going to be the pKa plus or minus 1. So that's going to be the pH range where it maintains that relative pH. And you would literally find the pKa, so do the negative log of Ka, and whatever that value is, the range that that buffer is going to work is plus or minus 1 pH value. So we're going to look at what most determines the pH range of a buffer is the pKa of the weak acid. So whatever that pKa of the weak acid is going to determine the range that it's appropriate for that buffer to work in. So when making a buffer, you want to choose an acid with a pKa almost equal to the desired pH. So you can use the ratio of the anion and then the parent acid and adjust it to be an appropriate value according to that pH. So here's the way that this might be asked. It says, which acid and its sodium salt would you choose to make a solution buffered at a pH of 4.25? And for your choice, calculate the ratio of base to the acid required to obtain the desired pH. So remember, it's going to be effective whenever the pH is within plus 1 or minus 1 of that pKa. So to choose the appropriate buffer, we want to find the one that has the closest pKa value to our desired pH. So if you look at chlorous acid, 1.95 is not within one pH value of 4.25. So it's not going to be chlorous acid. Nitrous acid, 3.34. It is within 1, so that is a possibility. Formic acid, the pK is 3.74, so yet again within that value of 1, so that's also a possibility. Hypochlorous acid has a pKa value of 7.54. That's more than 1 away from our desired pH. So then we're narrowed down to 2 options. Both could be used, but the more appropriate one is going to be the one with the pKa closest to the pH. So we would select the formic acid. Now to address the second part of the question, where it wants us to calculate the ratio of the base to the acid required to get that desired pH. So we picked formic acid, which had a pKa value of 3.74, and our target pH is that 4.25. So we can plug these into our Henderson-Hasselbalch equation and solve for the ratio of base over acid. So if we plug in the values we know, our pH is 4.25 is equal to our pKa, which was 3.74, plus our log of base divided by acid. So we would subtract the 3.74 to get 0.51 is equal to our log of our base over our acid. Remember to do 10 to the power for both sides to get rid of log. And then we get that base to acid ratio would be equal to 3.24. So we might add 3.24 milliliters of base for every milliliter of our acid. And that's how we would combine to mix that buffer. We'll be doing more practice with this, but check out the practice problems on our study review checklist.